we can go to the last talk of the session, which will be basically about some cable tree wiring problems, so benchmarking solver on real-world scheduling problem with a variety of precedence constraints. And I hope
welcome to our presentation on benchmarking solvers on the cable tree wiring problem. My name is Jana Koehler and I present the first part of this talk.
And my name is Sophia Saller and I will present the second part of this talk.
Cable trees are used everywhere in products. They are necessary to transmit energy and information between machine parts. You see here on the slide the picture of a car and where the cable trees are shown that connect various devices in the car. Each cable tree consists of so-called harnesses or housings that are equipped with several cavity openings into which the cables have to be inserted. By wiring the harnesses with these cables, the cable tree emerges. The production of cable trees mainly proceeds by hand. Today, 98% of all cable trees are manufactured by hand and only 2% are produced on machines. This slide shows on the left a picture of the manufacturing of a large cable tree by a human person. On the right, we see the automatic production of a smaller cable tree on a Zeta machine by the company Comax in Switzerland. Let's watch this video. You see here in this video how the machine connects the various housings by inserting cable ends into the cavity openings. There's a single robot arm that moves from the side of the machine onto the pallet where the housings are mounted. The cables cannot be plugged in an arbitrary order because otherwise already wired cables would block certain cavity openings or the robot arm could get caught in already mounted cables. Ongoing miniaturization and quality requirements drive the trends towards automation. It is not surprising that broken electrical contracts are the #1 cause of technical failures in cars today. Let's look more closely at the cable tree wiring problem on these Zeta machines. Given the specification of a cable tree, which is described by the harnesses with their cavities, given the geometry of these elements and the wiring plan for the cables, we were asked to create two solutions. First, a layout to place harnesses on the holding pallet of the machine, and second, to compute a sequential ordering or permutation of wiring steps for all the cables such that the machine operates safely, which means that the robot arm does not get caught in cables, and such that all cable ends can be plugged into their cavities. Here we distinguish two sets of different cables. We have so-called two-sided cables where both cable ends need to be plugged into cavities, and we have so-called one-sided cables where only one end needs to be plugged and the other end can freely swing around. As an optimization goal, the production time should be minimized. In the Constraints Journal paper, we consider the cable tree wiring problem for a given and fixed layout. This means that we assume that the layout was already computed and we are only looking into the problem of computing the sequential ordering of wiring steps. We defined the problem in this paper, and the CTW domain was also submitted to the Minisync Challenge 2020, where several solvers worked on problems from this domain. For this domain, we also compiled a benchmark set and put together a rather elaborate toolchain to test and evaluate various solvers. Both can be freely downloaded from GitHub. The wiring problem is a typical permutation problem. Let Ci denote the job of inserting cable end I into its corresponding cavity. Then for every two-sided cable, we define a job pair Ci-Cj, where the cavity Ci, so one end of the cable is numbered from 1 to B, and the other end of the same cable is numbered from B from B plus 1 to the end. Yeah, no, this is numbered. So J is numbered from B numbered by B plus 1 I. So for the one-sided cables, we only define a single job Ci, and these jobs are numbered after the two-sided cables ends have been numbered. So a one-sided cable end is numbered from 2B plus 1 to 2B plus n. Based on this encoding, we are interested in computing a permutation of length k, where k equals 2b plus 1. In this permutation, p of Ci is the position of Ci in the permutation P. The number of potential wiring sequences or permutations for a CTW instance is very large. For example, if we have 40 cables are given and both cables are two-sided cables, then we need to compute a permutation of length 80. In principle, there are 80 faculty possible permutations. And this creates a rather large search base. Among these possible permutations, only some satisfy the given constraints and are valid solutions. And among the valid solutions, only some are optimal. To model the problem, we developed different types of constraints. First, we distinguish atomic precedence constraints, which can occur in hard and soft form. The hard atomic precedence constraints must be satisfied, whereas the soft constraints incur a penalty if not satisfied. An atomic precedence constraints defines an ordering between two cavities. So a cavity Ci must precede a cavity Cj, and this means that the position of this cavity Ci must occur before the position of the cavity Ch in the permutation. We also introduce disjunctive precedence constraints, which are disjunctions of two atomic precedence constraints. They occur in a limited syntactic form and are defined over a job pair for a single cable and another job coming from some other cable. Finally, we distinguish direct successor constraints. So given a cable and described by a job pair Ci-Ch, a solution satisfies a direct successor constraint if the position of the cavity Cj immediately follows the position of the cavity Ci. So this means that once a cable end Ci is plugged, immediately the other cable end Cj of the same cable must be also plugged into its designated cavity. This is not necessarily the case for all cables. In general, the machine has the ability to store a cable end into a storage, so it can wire one end of the cable and then interrupt the job pair and continue to wire the other end of the same cable at a later point in the permutation sequence. In the paper, we discuss a possible optimization function. Using the storage in this machine leads sometimes to a delay in the production time. So that's why interrupting job pairs is highly undesirable. In our experiments and for the benchmark set, we use a weighted sum here of different criteria. For example, we count the number of interrupted job pairs with highest weight, then followed by the maximum number of cables which are contained in the storage, the longest time a cable end resides in storage, and finally the number of violated soft atomic precedence constraints. For our example and the solution C5, C3, C4, C2, C1, this cost formula returns cost 161. the value of the optimization criteria S, M, and N is 1, whereas L equals 2. So this solution is one of the 2 optimal solutions that exist for this instance. With this, I would like to hand over to Sophia Saller.
So in the paper, we considered 2 modeling variants for this problem. A non-dual variant, so a non-dual representation of the permutation, and a dual representation of the permutation. For the non-dual model, we simply have as decision variables the array position for cavity, PFC, which represents the permutation sequence. It uses as the cavity number as the index and stores the position of the plugging of this cavity number as the value. Then we introduce an all different constraint, which makes sure that all the values in this array are pairwise different from one another. And all the constraints, so all the soft and hard constraints and the optimization criteria are formulated over this array PFC. In the dual model, we then further add another array, cavity for position, which is basically the inverse of the position for cavity array. There we use as position the index, the position as the index, and store the cavity number as the value. The dual permutation representations are then linked via a channeling constraint. As an example, if we have CFP equal to 312 and PFC equal to 231, then these 2 arrays describe the same solution, where the cavity 3 is wired first, then cavity 1, and finally cavity 2. Here we now see an overview of the models that we used in the experiments and how the data files and the models are fed into the solvers. Note that the original models are the M and DM models, which you can see at the center of the slide. And we translated these models into equivalent or similar models for the different solvers and non-dual and dual models. The cable tree wiring problem is essentially a traveling salesman problem with atomic, soft atomic, disjunctive and disjunctive precedence constraints and Tor-dependent edge costs. So here the edge costs are not just dependent on the time, but they're actually dependent on the cavities that were wired before the current cavity is wired. It can also be seen as a variant of the pickup and delivery TSP problem, where the pickup and delivery correspond to the cables or the 2-sided cables. And the pickup and delivery locations can be exchanged, but they should not be interrupted, but follow one another directly. Finally, the CTW problem can also be seen as a variant of the coupled task scheduling problem, where the coupled tasks again correspond to the wiring of 2 ends of the same 2-sided cable. In the paper, we further provide a proof of the NP hardness of the CTW problem. In particular, the CTW problem with only soft atomic constraints and just 1-sided cables is NP hard. We prove this by a reduction from the maximum acyclic subgraph problem. On the other hand, we show that the CTW problem with only 1-sided cables and only hard atomic constraints can be solved in linear time. We further conjecture that the CTW problem is actually NP hard, even if we just have hard atomic constraints, but we also have 2-sided cables. The cable tree wiring benchmark set comprises 278 instances. Of these instances, 205 are real-world instances and 73 are artificial instances that were constructed by industry specialists to highlight specific challenges when wiring cable trees during the development of the solution described in this paper. 22 of these instances are unsatisfiable. And each of the instances is defined by the number of cable ends K, which need to be plugged, the number of 2-sided cables B, and its constraint set. Of these instances, only 20 instances have length smaller than 10. The majority of them, in particular 239 of them, have length between 10 and 100, and 19 instances have length over 100 and up to 198. The real-world instances, however, range between 20 and 50.
You see here a snapshot of the table that we put in the paper to describe parameters of some of these instances. And you see also here the number of soft atomic constraints, and disjunctive constraints. And furthermore, we also studied different parameters that were actually quite helpful to predict the difficulty of an instance.
We benchmarked the following solvers on this benchmark set, several CP-SAT solvers, MIP solvers, and OMT solvers. And here you can see how a real and artificial solved instance looks like in reality. And as I said, the artificial instances were constructed by industry specialists to highlight specific challenges. And finally, we present here some selected results for the tested CP-SAT solvers on the non-dual model. The paper further explores the sensitivity of the solvers to dual and non-dual modeling variants, leading to interesting results. As can be seen in this table, the Cplex CP and Google R-Tools CP-SAT solver outperform the other solvers, with Cplex being the only solver to find solutions to all instances, all solvable instances, and Google R-Tools finding more optimal solutions than any of the other tested solvers. Note that the benchmark set also includes two pathological instances, one with no cables to be plugged, so where the initial state, the empty permutation, is equal to the goal state. Further, an example with just a single one-sided cable and no constraints is included, which some solvers cannot handle. Finally, we can come to the conclusions from our paper. We have seen that the cable tree wiring problem is an interesting domain for benchmarking solvers. In the paper, we discuss various modeling variants and compare the performance of the solvers on these modeling variants. Across the board, however, the CP solvers outperform the MIP and OMT solvers, with especially the Cplex CP and Google R-Tools CP-SAT solvers showing superior performance. The CTW benchmark set is available online and comes with models and code to facilitate further experiments on this benchmark set. We further study parameters for the recognition of hard instances and phase transitions in the paper. And finally, CTW is a sequential domain where oftentimes many dead-end states emerge through side effects of sequences of actions. This makes the CTW domain a tough challenge for reinforcement learning algorithms. And with that, we come to the end of our presentation.
Yeah, thank you very much for your attention. We are available for questions.
Yes, thank you for your for your presentation. So Michael, so you have a question, so you can ask your question.
Yes, thanks. Very interesting problem, interesting presentation. I just have a small modeling question. For the disjunctive constraints where you have A is earlier than B or A is earlier than C, did you ever try A is earlier than the min of B and C, which I would expect would work better in CP solvers?
Yes, actually, for some of these disjunctive constraints, they can be reformulated, and the minimum function is used and also available in these models.
Okay, thanks.
Okay, so I would have a question. So
there's also another, yes.
Yeah, one question. In fact, I don't remember exactly, but some years ago, basically, there was, I think, I'm almost sure it was at CP Aware. So there was basically some presentation about some filtering algorithm, which combined basically all different constraints, the permutation, and also basically precedence constraints. So did you try to also because basically these precedence and the permutation constraints, they interact. So did you try to also to see what you could get better propagation by using this combination? So the dedicated filtering for this combination?
Well, we use different variants in the model where we used like the dual and the non-dual representations, and we also added all different constraints, the inverse or channeling constraint, some also making some constraints then redundant, and also experimented. But in this particular domain, we did not obtain a clear picture. Then we decided for one modeling variant, which was mostly best done on the majority of the instances, and we describe these issues in the paper in more detail.
Okay, fine. Is there any other question?
That's the last question.
Yes, okay. So thank you for
Okay.
Thank you for the presentation. So I just have a question about the comparison. So you use default configuration, if I understood well. And if you just did that for all solvers, did you also try maybe to do some tuning or?
Yes, actually we did. I mean, we have let's say a big set of experiments where we use the solvers in default configuration, but then mostly for the CP solvers, we also try to do some tuning, including, for example, search annotations in the mini-sync models.
Thanks.
Okay, then if there is no further question,
What was the result?
basically.
Okay, we have one more here.
Just a simple follow-up question. So what was the result?
Okay.
Oh,
Could you ask your question again then?
Yeah, sorry. So just a follow-up question to Nusrat's question. So what was the result of this tuning? So for example, search annotations, was there any search annotation that was particularly useful? Some parameter that seemed to be very important?
Yeah, not so much. There were some improvements, but they were not really significant. Actually, we were also surprised that some solvers are really also completely or rather independent of these modeling variants. For some solvers, for example, using the dual model makes a huge difference. For example, for Cplex, Google is not very sensitive to these modeling techniques. And also the tuning helped to boost the solvers a little bit, but not so much. And we tried a lot of combinations, nearly everything that is possible, in particular in the mini-sync search annotations.
Mm-hmm.
Sophia, do you want to add something on this paper? No. Okay.
Okay, thanks.
Thank you. So basically, yeah, maybe if there are some questions about the previous talk, because we didn't take any time for the previous question for the previous talk, if there was still some question for the previous talk, but okay. If not, basically, so we can close the session, and thank you for all the speakers and for the people attending the presentation, and those which basically make the travel to Vienna. So thank you.
Thank you.